recording. All right, so I'm going to do, I think for this session, I'm going to put in like two parts. The first part is do a quick review of lecture 7 to 10. So the exam number 2 will cover lecture number 7, number 8, number 9, and sorry, number 7, number 9, and number 10. Will not cover things in lecture number 8, which is ANCOVA, analysis of covariance. But I will just briefly review that, the lecture notes. So that's the first part. The second part will be after the break. We'll do 10 minutes break after the first part. The second part so will be like a question and answer. So you can answer any question regarding the lectures and also the homeworks. But in the first part, I would just go over the key thing in the previous lectures and in lectures, in the things I will cover in the exam number 2. All right.
All right.
I just make sure everyone can hear me because it looks like everyone mute except you mute their microphone.
Yeah, I figured I'd get on camera.
And
I can hear you.
yeah.
Yeah, I hear
Okay.
you fine.
Yeah, we're good.
Yeah, I just take off my video because if not, my internet gets very slow.
Oh, okay. All right. I just make sure everyone can hear me and can answer questions. So anytime you can answer question. And also I figure out the share screen thing. And now I allow multiple participants to share the screen. So in case if you have any question you want to share your screen, you can do that. But that will be primarily in the second half, the Q&A session. All right. So if everyone's ready, I'm going to share my screen. So, so the first thing I want to let you know is I'm posting the exam number 2 under assignments. So you're going to see the exam number 2 take home due next week. So basically have 1 week to do this take home exam. So it's available at 5 p.m. today. So it's right after this session, you will be able to see that. So my view is different from your view. So you'll be able to see my questions in the PDF file. And also there's a data set called exam number 2.SAS data. But let me know if you cannot open the SAS data. If you prefer to use a CSV, I can also post a CSV, but I hope you to do this in SAS because I mean, that's part of the goal. Let me know if you can. Yes, go ahead.
Would it be possible, yeah, to add another format that could be used in another, like SPSS, for example? Like people with Macs are having a lot of issues opening SAS.
Mm-hmm. I can pull the CSV. CSV, you can open the CSV using SPSS or using Stata or using whatever thing. Well,
Thank you.
Yeah, I will post a CSV. All right, and so I think in terms of the exam questions, so if you cannot, I mean, this time of day, if you cannot have a computer which can use a SAS, let me know. I may figure out something else for you. All right, so that's for the exam. Okay, and then I just want to quickly go over the previous lectures. And at any time if you have a question, just stop me and ask a question. All right, I think I have to stop the sharing screen and change the sharing, just let you know. All right. All right. Okay. Okay, I'm going to starting from lecture number 7. Can you still see my lecture notes right now? Lecture 7?
Yes.
Yeah.
Okay, perfect. Okay, I'm just going to quickly go over. I only go over the things which will be covered in the exam because since I have the exam questions ready. All right, so for the first part of lecture number 7 is the one-way ANOVA. So lecture number 7, actually I put into 2 big sections, part 1, part 2. Part 1 is a one-way ANOVA, part 2 is a two-way ANOVA. So the difference between the two is one-way ANOVA, you only have one factor. You want to test the factor on the mean of a continuous variable. Two-way ANOVA, you have 2 factors. So once you have more than 2 factors, there will be an interaction. So it's more complicated in two-way ANOVA because you not only to consider the main effects, but also you need to test the interaction between the 2 factors first before you can finalize your model. All right. So the one-way ANOVA, what I want you to know, the first thing is the goal. The goal of that is to test the difference in the mean of a continuous variable. So remember, the outcome variable has to be continuous. But we're not testing we're not comparing, like do 2-group comparison. This is going to be a t-test, right? So we're going to test on a factor which have more than 2 categories. Or like say 3 or more categories, what has 3 or more levels. And the goal is going to be 2 goals. One is to see if across these levels, the mean of the response variable or the dependent variable, or we call the outcome, will be the same simultaneously across all the levels. The other part is what we talk about as the multiple comparison. So multiple comparison has to be done only after you do the ANOVA. Because if you reject the null hypothesis in ANOVA, you're going to know that there at least one pair of the levels will have a different mean. So only if you reject null hypothesis, it makes sense to do the multiple comparisons. Because if you fail to reject the null hypothesis, you don't need to do the multiple comparison because you know all the groups have simultaneous equal in terms of the mean value of the response variable. So that's the goal of the one-way ANOVA. And also in terms of the specific question, you'll be able to write on the hypothesis, the null hypothesis and alternative hypothesis. So null hypothesis always you have mean, the mean of the first group equal to the mean of the second group all the way to the last group. And the K is the total number of levels or total number of groups defined by the factor. There's all going to be one factor in one-way ANOVA. And the alternative hypothesis is this is not true, which means at least one pair across these levels are not equal in terms of the mean. The assumptions, you can know this. I mean, you can just keep in mind the key assumption is independence. And also we require normality, but t-test is robust. I'm sorry, the ANOVA is robust to the normality assumption. And also there's equal variance assumption, but as I said, it's also robust to that. All right, and in terms of the mathematical models and the ANOVA table, so I want you to know to write down the model. So the model is you will have a mean of each group, which is equal to a grand mean plus the mean difference across each individual group. And also the key things is you can interpret this one-way ANOVA table in terms of the model. So basically you will have evaluation for the model itself. In the model, because you only have one factor, so the model testing is the same as you test that one factor. If you factor have K levels, and then the degree of freedom is K minus 1, because if you fix K minus 1 group, the other group is automatically determined. And there's one key test is the F test for the model, or it's the same as the one-way F test for the factor itself, because now factor is the same as the model. The model only has one factor. the F value is determined by the mean square of the treatment and also the mean square of the error. So the mean square of the treatment is equal to the sum of square for the treatment, SST. This is the same as the sum of square for the model or sum of square for that factor, divided by the degree of freedom, which is k minus 1. And the error will have a degree of freedom n minus k. The reason is you have n minus 1 for the total. And the n, remember, is the total sample size. And n minus 1 minus k minus 1 end up to be n minus k degree of freedom for the error terms. So your mean square error is equal to the sum square for the error divided by the degree of freedom n minus k. So a ratio between the mean square for the model, MST, and mean square for the error, MSE, is equal to the F value. And remember, the F value or F distribution will have a 2-dimension of degree of freedom. And you have a numerator degree of freedom, which is k minus 1, and error degree of freedom is n minus k. And therefore, this F value should be compared with the critical value for the specified test level, usually that's 0.05, for F distribution with denominator degree of freedom n minus k, numerator degree of freedom k minus 1. Well, that's the way. But if you use SAS, I mean, I won't be able to let you to do this in a take-home exam. But in the take-home exam, you can using, you'll be able to using SAS to run it, and you can directly interpret this F value in terms of the P values, because you automatically get the P values determined from the F test. But you should be able to know that this F value from the ANOVA table should be compared with the critical value of the F distribution with 2-dimension of degree of freedom. And numerator degree of freedom is k minus 1, and the denominator degree of freedom is n minus k. All right, is that clear, or any questions so far? So if no, we go to the next part, which is the t-test for the one-way ANOVA. The F test is the testing for the model itself. So even though this is equivalent to the testing of the one factor, because you only have one factor, testing the model is the same of testing the one factor itself. But there's still another test for the one factor itself. In SAS, the procedure called PROC ANOVA. So we do use two procedures. The first procedure, PROC ANOVA, is for one-way ANOVA. But you can also use PROC GLM. But PROC GLM usually used in two-way ANOVA with interactions. But in one-way ANOVA, it's sufficient. You just use PROC ANOVA in SAS. And you can specify the data resource, and then you need to specify the one-way factor, the only one factor as the class variable. So class variable means you specify this variable as a categorical variable. And then in the model, you're not going to treat this variable as a continuous variable, because this is a continuous variable, you're going to have a different result. So if you specify the factor as the categorical variable, and then the degree of freedom is just k minus 1, like in the example in lecture number 7, because this age group have 4 levels, and therefore you have 3 degree of freedom for that test. And the SAS will output the ANOVA table as I show in this. It's basically the same configuration, the same display, but you just need to explain this in terms of the specific question, in terms of your study question. So like say in this question, you have 3 degree of freedom for age, and then you have the sum of square for age, and the mean square error is equal to the sum of square divided by the degree of freedom. So basically it's 2891 is equal to 8674 divided by 3. In error terms, SAS already gave you the degree of freedom, which is total minus the model degree of freedom. And SAS calculated the sum of square for that part. And this divided by the degree of freedom is equal to mean square error. And then this F value is equal to the mean square for the model divided by the mean square error. So which is to say 41.5 is equal to 2891 divided by 69. And this F value, you have to compare that with the critical value from the F distribution with the numerator degree of freedom equal to 3 and the denominator degree of freedom equal to 60. And then you compare this, you'll be able to get the p-values. So either you can do the hypothesis testing by comparing with critical value, or you can calculate the p-values from this F score based on the F distribution with these two degree of freedoms. All right, this is going to be the model you use. So remember this model. So this model means you assume across this group there's a grand mean. The grand mean mu is interpreted as the mean of y across all the groups. So this is basically just the group mean. You're adding up all the group mean together divided by the number of groups. And this is also equal to the sample mean, so which is the each individual observations, sum them over divided by the total number of observations, which is also equal to this mu. And this alpha I is interpreted as the treatment effect. So if you factor is the treatment, so this alpha I is the differential effects of i's treatment from the grand mean, from the mean mu. So which is to say, what's the deviation of each specific treatment group from the grand mean? Like say, if you have a better treatment, you may have a better value. So that means, and therefore you can see this group effects or treatment effect. And alpha is equal to mu minus the group mean. And this mu1, mu2 to mu k is equal to the mean in group 1, group 2, all the way to group k. All right, and then I just quickly go over this this example. In this example, we have the 4 age groups, and then for each age group, you have this total different number of observations. And usually after you run a one-way ANOVA, we'll be able to calculate the group mean because the group mean is actually, if you use this equation, but you can just like rearrange a little bit to see that the group mean. So the group mean mu1 will equal to mu minus alpha 1, or mu minus alpha 1, and mu2 will be equal to mu minus alpha 2, something like that. So SAS will calculate in that way. So if you use the means statement in the procedure ANOVA, so ANOVA and SAS will output this estimated mean at the end, and with the standard deviation and the sample size. Okay, so the next part is the multiple comparison. So as I said, the multiple comparison only be conducted after you do the one-way ANOVA. So only if you reject null hypothesis, you know, at least one of the pairs is not equal in terms of the mean, and you will do the multiple comparison. Because if you fail to reject the null hypothesis and you know all the group will have the same mean, you should not do the multiple comparison. And you can still do that, but the thing is not meaningful to do the multiple comparisons. So multiple comparisons is only if after you reject null hypothesis. And I talk about 3 different ways to do the multiple comparison. So the Bonferroni is basically just looking at testing a specific group comparison. And then the way to do that is you will not change your score. You're not testing score, something like that. The way you change is you will change your p-value to be compared with. So that is equal to the the test of the Bonferroni test, the test level is equal to the total test level 0.05 divided by the number of tests. So for example, if you use 0.05 as the test level in a regular test, but the multiple comparison will give you 10 tests. So now your p-value, not the benchmark for the p-value is not 0.05, it's 0.05 divided by 10. So that's going to be 0.005. Okay, and as I said, this is specific for a testing, not exhaustive number of pairwise comparison, but it's very good for testing a specified comparison. Like say, for example, in this in the age and systolic blood pressure example, if you're only interested in testing group age group 1 and 2, and the group age 3 and 4, so you will use this Bonferroni test because you're testing these two together, and then the adjusted Bonferroni test level will be 0.05 divided by 2, which is equal to 0.025. And then you can, based on this, to have a 95% confidence interval as well. All right, the second one we talk about is this Tukey-Kramer method. So this is specifically useful for testing the exhaustive number of comparisons. So for example, if you have a K levels, the total number of pairs is K choose 2. So K choose 2 is equal to K times K minus 1 divided by 2. So this is the total number of a unique comparison across these groups. And the way to do that is you can create the exhaustive number of pairwise comparisons. So for example, if you have 4 groups, 4 choose 2 is equal to 6, and you can write down all the pairwise comparisons. You can compare age group 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, and 3 and 4. So it's exhaustive number. And then the way to do that is you do a test simultaneously, and you see which hypothesis will be rejected and which hypothesis will not be rejected in this group testing. In SAS, you can use the option Tukey, but that has to be in the means statement. It's not, remember, that's not in the model statement. That you have to put in the mean statement. And means you have the factor, which is the one-way factor in ANOVA. So in this example, it's age. And these Tukey options in the mean statement will run the Tukey-Kramer multiple comparison. And also you can ask for a 95% interval, which is the CL indifference. And here you will specify the nominal alpha level. So usually we'll use 0.05. But the way is SAS, when you use this Tukey method, it will adjust for similar as the way to adjust for the test level alpha as in Bonferroni, but it's a different way. And then what you got from the result is a pairwise comparison table. But remember, SAS will give you the pairwise comparison table. The number of comparisons is more than 6 here, right? It will put every single comparison. It will just double the number. The reason is, for example, the comparison between 3 and 4 and 4 and 3 and 3 and 4 are actually equivalent. The only difference is the sign. So this will use the mean of age 4 minus mean of age 3. This will be using mean of age 3 minus 4, but actually they're equivalent. They're not, though these are not unique testing. So you need only keep one for the unique testing for that. And also the 95 interval is just a reverse. So they're going to give you like 12 tests because there are redundants, like say 3 and 4 and 4 and 3 are redundant. Only difference is the signs. So you will be able to pick out all the unique number or the unique comparisons. Like say if you do 4 and 3, you can pick up 3 and 4. So the unique here will be 3 and 4 and 3, 4 and 2, 4 and 1, 3 and 2, 3 and 1, and 2 and 1. So all the others will be the redundant as the other information. All right. The next one is the Shaphase. So Shaphase is kind of like a flexible comparison. It's not you just compare the mean, the group mean for across different levels, but you can do any combinations of the mean. So for example, if you want to test if the group mean for the first age group is equal to the average of the other 3 age group, you can do the test like that to see if mu1 equal to mu2 plus mu3 plus mu4 divided by 3. Or you can write down as linear combinations. The way to do that in SAS is actually using this linear combination, but you give a coefficients in each of the group mean. So like here, the group mean C1 will be 1, or the others will be negative 1/3, something like that. And the Shaphase master will give you the 95% interval for the linear combinations of any group means. And also it can give you the it can give you any so it really depends on your hypothesis. So if you have multiple hypotheses, you doing them together, it will give you the 95% interval for each of the hypotheses. Like in this example, we have 2 hypotheses. One is to see if the average of group 1 and group 2 is equal to the average of group 2 and 3. The other is to see if the group mean of the first age group is equal to the average of the other 3 age group. And each one you will have a 95% confidence interval, and I'll give you all the equations. So if you do not have a computer, you have to calculate this way. But if you use SAS to get results, SAS will automatically just output this result. So you have to use the proc GLM to do this instead of proc ANOVA. So keep in mind you have to do a GLM if you want to do Shaphase, or if you want to do the testing, we call it contrast instead of a group-wise comparison. So for example, if you compare group 1 with the other 3 groups, average with the other 3 groups, so you have to use a contrast statement and you go give coefficients for any one of them. Or you can use the estimate statement and you give a integer number. But here in the contrast, you can give any number. But if you want to use the estimate, you have to give integer number and then give a divisor. But they end up to be the same thing. The p-value will be the same, but this contrast will do f-test, and this is part of partial f-test. But this, if you use estimate statement, it's going to be do a t-test, but they are equivalent, and you can calculate that f value is equal to the square of the t values. All right, so that's the Shaphase, and this is everything for the one-way ANOVA. So I'm going to go to the next one. Which is two-way ANOVA. Can you see my lecture notes for part 2?
No, I just see the test single contrast in SAS.
Okay, and then I think I need to.
Yeah, you have to press share screen again.
Create square and share one more time. All right.
Yeah.
Dr. Hu, I have a question.
Go ahead.
So for this same model that you're using here, let's say that you were testing another hypothesis. Let's say that you're doing mu1 and mu2 compared to mu3 and mu4. How would that differ for the prog GLM code for SAS? How would that differ in the value? How would it be different in the values of like 1, -0.33, and so on?
Let's go back to that page.
That's the page that's still showing up.
Yeah, the page that you're on right now. Test single contrast in SAS.
This one?
Yeah. Mm-hmm.
All right. So your question is, what's the difference between this and this? Is that right?
No, no. My question is, if you were testing H for group 1 and 2 versus 3 and 4,
Mm-hmm.
what would it look like for the values that you're assigning for each variable? Like
Gotcha.
say, okay.
Gotcha. So here it'll be one half for the first age group and one half for the second one, and negative one half for the third, and negative one half for the fourth.
Okay.
So if you use estimate, it's going to be 1, 1, negative 1, negative 1, but your divisor is equal to 2.
Okay, sounds good. Thank you.
All right. Any other questions? So if no, I'll stop sharing for this and share the next one. Okay, looks like it's still on the same one. Let me see how I can, probably I need to close this one first. All right, and see if we can find the second part. Okay, so the second part is the two-way ANOVA. So as I said, two-way ANOVA, you have at least 2 factors. So we call factor A and B. So now you're going to test 3 effects. One is the main effects of factor A. The other is the effects of factor B. And the third one is the interaction between A and B. So whenever you have more than 2 or more effects, so you have to worry about the interactions. So this is very similar to when you do a multiple linear regression, you have to worry about the interaction term. All right. Okay, so the interaction terms is basic to see if the effect of factor A will be the same in the 2 different levels or more than 2 different levels of factor B. So that's the goal. So if they're not the same, that means you have to keep the interaction terms in your final model. And you have to remember that there is interaction. That means there is a systematic difference in terms of the different levels of another factor for the relationship between one factor and another factor with the outcome variable. So the graphical interpretation of these interaction terms is if they are parallel, approximately parallel, between the 2 groups for the relationship between the response variable and the other factor. So you will see there's no interaction. So this is graphical judgment. So this is not accurate or there's not the statistical based, but this is just graphically, you can approximately judge the interaction in this way. And a very obvious indication or feature of interaction is if you see the crossover of the 2 groups. So this will give you an indication that there's going to be an interaction between the 2. And then you can do a formal test for this. But if you see the 2 groups have approximately parallel shape of the relationship between the response and the other factor, and there is, at least give you some evidence, there may not have a significant interaction problem in this, in the two-way ANOVA. And here's the two-way ANOVA model. So here you will have an effect of the first factor, which is given by this alpha I, and also by the second factor, which is given by the beta J. And the J is the indication of the level for factor B. I is the indicator of the level for factor A. And in both factor, you should have more than or equal to 2 levels. And the key thing I would say, because this is something really different from one-way ANOVA, is the interaction between alpha and beta. And there you're going to use 2 subscript I and J to indicate that in the interaction terms, because this interaction, the value of interaction is not only determined by I, but also determined by J. And then you have error terms determined by I, J, and K. I is the level for factor A, J is the level for factor B, and K is the index of the repeated measurements for that group. Like say, in each combination of the factor A and B in that cell or in that group, you need to have a multiple replicates. So without replicates, you're not going to have a variance. You cannot do ANOVA because ANOVA is based on the variance partition. And here you need to have at least some replicates. And this is why you use the K. The K is just the indication or the index for the replications inside each group, defined by factor A and factor B.
Dr. Hu, is there a minimum of replicates that you need to have to run the ANOVA?
I think the minimum is 2, but if you have 2, you may not have very accurate or you do not have a power to do testing for that.
Okay.
But the minimum is 2. So
Okay.
if you have 1, there's no replicates, right? There's no variance at all. The group mean is equal to the observation mean. There's no variation. And then you won't be able to partition that variance.
Okay. Okay. Thank you.
Yes. Where would it show up in the output? How many replicates were used in the analysis?
So I will show later, but so if you remember in one-way ANOVA, so one way do the mean, and then you have that mean table for each age group. Remember that? They give you an N there.
Okay.
So for example, the first age have 14, the second have 18, third have 18, something like that, if you still remember that table. But it's not in the ANOVA table. It's in the estimated mean table, but not ANOVA table. ANOVA table will not give you that. ANOVA table only give you the degree of freedom for each factor. All right. So this is the two-way ANOVA table. As I said, this ANOVA table. So the only thing you have is the degree of freedom and also the sum of square. The sum of square is very similar to the variance. So the partition of the sum of square is equivalent to the partition of the variance. And that's the thing for the key thing for ANOVA. Because this is not a theoretical class, so we're not going to cover too much about the theories or the statistics and mathematics there. But usually, like ANOVA is whole class for one semester. So if for that class, you need to learn that what's the specific calculation for that, and what's the rationale there. But here, you just, I think the key thing you just remember this two-way or one-way ANOVA table and what each term represent. And here for each row of A and B, so you have a degree of freedom. And again, the degree of freedom in two-way ANOVA for each factor is still the total number of levels minus 1. So if your factor A has alpha level, so degree of freedom is alpha minus 1 for that. And B is B minus 1, B is total number of levels for factor capital B. And then because we do the partition of the sum of squares, we have the total sum of square. And then the partition of total sum of square will give the sum of square explained by factor A, which is the SSA. And also the sum of square explained by factor B, which is SSB. And also the sum of square, which is explained by the interaction A and B. And then we also have the degree of freedom. The reason we need the degree of freedom is we need to calculate the mean square error, and also we need to calculate the F-score. The total number of degree of freedom is n-1. It's the same as in one-way ANOVA, because so if you specify, if you have a mean and then you specify n-1 terms, you automatically specify the last terms. The value is automatically determined. The error term will have a degree of freedom equal to n-8 times b. So it's easy to understand that because so if you have two factors, one factor have a total number of level A, the other have total number of level B. So total degree of freedom occupied by row thing is A times B. Just like if you do a in A times B table. So it's easy like 2 by 2 table. The 2 by 2 total 40 degree of freedoms. But if you have an A times B table, so you have A times B degree of freedom, which is occupied by all the factors. But if you further partition that degree of freedom, you can see each factor, actually the main effect will have the degree of freedom equal to the number of groups, -1. And interaction will have A-1 times B-1, just equal to the product of the levels -1 in each of the two factors. And here, you can actually easy to see that from the result I will show later, because like say for each level, for the interaction terms, you always have a reference group. So you will tease out that reference group for each part, and which end up to be A-1 times B-1 terms, which really have the values, because the reference group, you won't have a value for that reference group. And therefore you can see total values for that interaction term is A-1 times B-1. And the mean square error is equal to the mean of square divided by the degree of freedom for error, and the mean square for each factor is equal to the mean square, the sum of squares divided by the degree of freedom for that. So it's explained by the average sum of squares for each degree of freedom is the mean square for the factor and the mean square for the error. And the F-score here is equal to the mean square for each corresponding factor divided by the mean square error. And here you can see we have 3 effects as we introduced in the previous slide. An effect for A, effect for B, and effect for A and B. So you need to have each mean square for that factor divided by mean square error. So the mean square error is always the denominator for that F value. And then you are going to compare this F value with the F distribution at the critical value for the corresponding 0.05 test level. But this F value should be compared with the F distribution with the numerator degree of freedom equal to the corresponding degree of freedom for the factor, and the common denominator degree of freedom, which is equal to n-8 times b. So for example, the first test, you will have a numerator degree of freedom n-1, A-1, denominator degree of freedom n-ab. The second will have numerator degree of freedom B-1, denominator degree of freedom n-ab. And this one will have numerator degree of freedom n-1 times B-1, and the denominator degree of freedom n-ab. So that's the key thing. I mean, just in case if you calculate that by hand, this is very important. Degree of freedom is very important because you need to identify the F table and then which table you should use to get a critical value. But if you're using software, like using SAS, using Stata, using SPS, and you won't be able to work that too much because the software will automatically calculate the p-value based on this resultant F-score and also the F distribution for the corresponding degree of freedoms. They actually SAS already use that information, but you don't know they actually use this information. But if you calculate by hand, this is going to be very important. All right, so that's for the F test for factor A and B and the interaction terms. So if you want to use a SAS for the two-way ANOVA, so we're going to use procedure called GLM, general linear model. And then you have to specify both factor as in the class statement because they both are categorical. But in the model statement, you should start with the model with main effects of the first and second factor, as well as the interaction between them. So in SAS, if you want to specify interaction, the way to do that is to put a star. So like in this example, the SMK star age will automatically specify the interaction term between smoking status and age groups. So it doesn't matter regardless of how many levels you have in these two factors. So it's automatically create all the interaction terms between them. So you don't have to, so remember you don't have to create the interaction term before you do that, like you do that in using prog-reg in the regression, linear regression. But here, if you want to use GLM, you don't have to create interaction terms. If you just use the star in the model statement, it automatically includes the interaction terms between smoking status and age in this example. And this means a statement we're asking for the mean, the estimated mean for every single combination of the smoking status and age group. So I just wanted to, it's important for you to be able to interpret the result after you run this prog-GLM for two-way ANOVA. The first one is the ANOVA table for the whole model. So you can see they put all the degree of freedom all together in the model. So which means this model including all the effects, including the main effects for smoking, main effects for age, and also the interaction between them. And then you only have one error terms there. And error terms is just everything you tease out, partition the sum of square into a sum of square explained by the whole model. And also the sum of square explained cannot be explained, which is the error terms. And then you only have one F value in that case. So that's the F test for the model as a whole with all the 7 degree of freedoms. And the next one is you really testing for each factor because this is a further partition of the 7 degree of freedoms. So it will distribute 1 degree of freedom for smoking because smoking have two status, yes and no, and 3 degree of freedom for age because age have 4 groups. And also 3 degree of freedom for interaction because interaction equal to parentheses 2 minus 1 times parentheses 4 minus 1, so which is equal to 1 times 3 is 3 degree of freedoms. And this is very similar for the partial F test. So this is the F test for the whole model, and this is the partial F test for every single degree of freedom. And it's not for every single degree of freedom, it's for every single factor. Because some factors have more degree of freedom than the other factors. Smoking only have 1 degree of freedom, but the other two have 3 degree of freedoms. And also SAS output will give you the R square value. So this R square again for the whole model as a whole. And also they have the mean, they call it SPB mean, which is the grand mean, we call overall mean. So that's the mean for all of the 64 observations. So you sum up the 64 observations, the systolic blood pressure for 64 observations, and they divide it by 64, which is equal to this 144. All right. And the next one is the type 3 sum of square. Is, as I said, this is further partition of the the sum of squares from the total sum of squares, because this total sum of square is equal to, no matter it's type 1 or type 3, so the total sum of square is equal to sum over the sum of squares for each factor. So we usually keep focus on this type 3. We don't worry about type 1. Usually we'll use type 3 because type 3 is interpreted as the effect of that corresponding factor when added to the model last. And this sum of square sum up to the total sum of square here is a further partition of the variance, or a partition of the sum of square. And then once you have the mean square for that each factor, and then you still use the error terms, the MSE here, right? Because this table will not give you error terms, but the F value being calculated is actually using this mean square for each factor divided by the sum of square for error, divided by 53 for every single F test there. But it won't show in that corresponding table in the SAS output. And then if you match this, this is a little bit different display as I show in this in this mock table, because in this mock table you actually have the error terms there, but in the actual SAS output they won't give you that error terms in each effect testing. They only give you that in the OR test of the whole model. But you should be able to know how this F value comes from. It's actually equal to this value, 1096 divided by 53.2. So it's about 20.6, right? And this 55.6.9 is equal to 2974 divided by 53. And similar for that interaction terms. All right, so that's the testing for each factor, and each factor may have more than one degree of freedom. And the next table is really like, say, the testing for each degree of freedom, right? So each degree of freedom, like say, for example, in the smoking data, you have 1 degree of freedom, but you have to choose one as a reference group, and therefore you only have one parameter estimate. So which is the smoking, non-smoking, smoking 0 compared with the smoking, because you use the smoking as a reference group. And age, you will have 3 parameters with that 3 degree of freedom, because you choose one as a reference group, and therefore you will have the other 3 to compare with the reference group. And also for the interaction part, you have 3 degree of freedom, if you still remember. So that's equal to parenthesis 2 minus 1 times parenthesis 4 minus 1, so which is equal to 1 times 3. That means you should have 3 parameters to corresponding to each degree of freedoms there. And then you can see you have three estimated values for the interaction terms. So the interaction for smoking equal to 1 or equal to empty is not relevant, because you choose the smoking equal to 1 as a reference. And just another one as the empty, which is NA, is the age equal to 4, because you use age equal to 4 as a reference group. And therefore you also have 3 parameters estimated for the interaction terms. And this you can consider as a further partition of this ANOVA table. So like say here, it just show you 3 degree of freedom altogether as one test. But here they will test each degree of freedom in age. And also attach each degree of freedom for the interaction between smoking and age as there. And you can see, for example, the age 3 degree of freedom as a whole, the testing of that, you got significant p-values. And then for each degree of freedom, you also have significance. So that means compare with age group 4, which is the oldest group of patients. So the systolic blood pressure are all significantly different. The testing for the interactions is similarly. So this is a p-value for each degree of freedom for the interaction instead of you putting all three together as a whole. And here you can think about, it's similar to your further partition this 3 degree of freedom into one, every degree of freedom you're testing on them. And here is the last one. So remember in the statement, we put this mean statement for the interaction terms or the interactions between smoking and age. And therefore it will give you all the combinations of smoking status with age. So you have a 2 status for smoking and 4 for age, and there are going to be 8 different groups. And for each of the age groups, it actually gives you the mean for the systolic blood pressure with the outcome and standard deviation for that. And this standard deviation is actually the standard error because the standard deviation of the mean is the standard error, but it just use the standard deviation. But you need to keep in mind that's the standard error for SPB. And again, also the number of observations. This is what I said, replicates. And like say, in that combination, you have 6 replicates. You can also call this number of observations or sample size within that age group, within the group between age and smoking status. So that's all. I think if you can interpret all of this, that'll be sufficient for the two-way ANOVA. I think the key thing is to interpret the each degree of freedom there, and also you need to know what does the interaction means. So the interaction, so why you need to do the test for the interaction. And the other important thing is when you want to finalize the model, you need to test the interaction term first. So for example, if the interaction term here, in this example, which is not a significance because the p-value greater than 0.05, so in your final model, you should remove the interaction terms, and then you need to rerun the model with only include the 2 main effects, include the main effects of age and the main effects of smoking. And then you should not include the interaction term in your final model. All right, here is so the SAS test for that. And the other thing is after you run the two-way ANOVA model, you should be able to get the, we call it a scatter plot, but it's actually connected by lines. It's not completely scattered. So there's a 2 way you can make this plot. So you can plot the response variable SPB with either factor, because you have 2 factors. So the first one here, for example, is you plot systolic blood pressure with the age groups, and then you have 4 age groups, 1, 2, 3, 4. You only have value at the integer 1, 2, 3, and 4 because this indicate groups. And then you will have 2 groups because that's 2 groups specified by the smoking status. And you can see in this example that this almost parallel, right? It's not exact parallel, but it's approximately parallel. So this is, if you first plot this, you can actually plot this before you run a two-way ANOVA test. And then you may have an idea, like say, there's not going to be a significant interaction between age and smoking status. So similarly, you can plot the systolic blood pressure with smoking status. So remember, I only have value at 0 and 1. They don't have value somewhere else. So even though you connect the 2 values. So only have value at here and here. And all the other in the middle are not relevant. But here you will have 4 groups. Each group will represent each age level. And you can see it's still like almost parallel, but not perfectly parallel. So which also prove that there might not be a significant interaction just from this visual display. All right, so that's the two-way ANOVA, and I also talk about the specific design of, we call this randomized block design. So this is kind of like, this is a specific example of the two-way ANOVA design. It's kind of like a design, you have one factor specified first in the block. So we'll have a block effect, and also you have a treatment effect, but you randomly assign the treatment within each block. And then you have a block effect and treatment effect and something like that. But usually are not interested in the block effects. You're only interested in the treatment effect. It's not exactly the same as the two-way ANOVA, but it's kind of like two-way ANOVA because you treat the block as another factor. But as I said, usually we don't interest in the block effect, only interest in the treatment effect. And this is just a specific example there for the petition, and I show you from one example. But this will not be included in the exam. All right, so that's all for the two-way ANOVA. Any questions? So if no, I'm going to go to the next part. I'll just quickly go. So the lecture number 8 for ANOVA, and that's the covariance and COVA will not be included in the exam, number 2. And this is an optional topic because I used in previous years when Dr. Lee taught this class. It's also an optional topic. I just keep that. The way you understand this, and as covariance, is actually this is a combination of the ANOVA and with a covariance. So remember, an ANOVA is you testing the factor effect, and that factor have multiple levels, but you do not have a continuous variable. But ANCOVA is a combination of the ANOVA, so you have a grand mean here, and then you have a treatment effects. I use tau I here, but you can also adjust for a covariate xij, but this xij is an continuous variable. So this is similar to a combined linear regression, because this part is more like linear regression with ANOVA. So it's useful only if your experiment is not totally randomized. So for example, so if it's perfectly randomized in the study design, you don't have to worry about adjustment for the covariance. But in some situation, you may not have perfect randomization for your study design. And you might want to control for some other factors, and then you can use this way. So one typical example, as I show there, is the pre and post analysis, because you can think about the outcome as the post measurements, and the X as the pre measurements on the same subject. So if you want to adjust for the difference in baseline, and then you can adjust and you can use the ANCOVA. So for example, you still measure you want to look at the different treatment on the blood pressure control. So you can measure your blood pressure before you use the treatment. And then you can also measure the blood pressure after you use the treatment. And therefore, you can use the after treatment as the outcome and before the treatment as the baseline or as the covariance. The reason you want to adjust for that is you might enroll the study cohort, which may not be perfectly randomized. That means there is a baseline difference in the blood pressure, and baseline difference may contribute to the bias estimate of the treatment effects. So for example, because if you have a higher blood pressure, you're more likely to be used for a new drug than using the standard of care, for example, and this will miss out the treatment effects. So this is called the baseline, or called the selection bias. So ANCOVA is somewhat very useful for that situation, to control for the selection bias. So this is a specific one I posted there. We call the pre and post study. And I actually divide it into a randomized versus non-randomized study. But randomized study, you only need to worry about is the efficiency, because with different type of analysis, we'll have the same result. But in COVA, it's actually is the most efficient because they give you the highest power as the same sample size, or I say this at the same power, it need the least number of observations. But this will be optional thing, so not be included in the test. But I just want you to understand. So if you're interested in knowing that, you might go over this lecture notes and also ask questions. In case you have any question, you can ask me. All right, so that's for ANCOA. So next one is we call the polynomial regression, and here the regression is still kind of a linear regression model I'm using. Is your outcome is continuous variable, and the predictor variable x is also type of continuous variable. And the goal here is sometimes you do not know if the linear terms of the continuous variable of the predictor variable is the best for prediction of the outcome. So that means maybe the quadratic terms or cubic terms are more even relevant. And you want to just know if we need to add these higher order polynomials into the regression model can help you to have a better prediction of the outcome. All right, so generically, so if you have a higher order up to k, so the regression model can be written like this. And here we only have one observed predictor variable, which is x, and all the other thing will be a higher power function of this x. Okay, so it can always from the first one, which is the linear term, to the highest order s to the k, and this including case order. This is called a case order polynomial model. All right, and the example I'm using here is actually using another systolic blood pressure, which is we use in lecture number 2. So we have the blood pressure and the age, which is continuous variable. This is not a categorical age as you use in the ANOVA lecture number 7. This is the continuous age. So we're texting actually using the linear terms and the quadratic terms of age. So here, actually, I teach this lecture. I want you to first to check outliers or influential point. This is very similar for the things as you see in testing the for model testing, we call model diagnostics for linear regression model, because you need to first pick out the influential point of outliers to be able to have a better model. Because the whole goal, the reason you need to worry about the outlier here is the polynomial is for better model fitting. So for better model fitting, you need to check the outlier and influential point, right? Because the influential point and the outlier may impact the model fitting. So you don't have to worry about this in other things like in ANOVA, you don't have to worry about these outliers because you're really doing association. But here you are looking at the predictions. This is why you only need to have to worry about outlier here in the polynomial regression. So in this example is actually we're testing if the quadratic terms of age is significant or can better improve the prediction of your model, what we call improve the prediction power for the model itself. So I think the key thing here you have to remember is if you use the quadratic terms with the linear terms and put them all together, and you know the linear terms and the quadratic terms may be highly correlated, So this can be seen from the Pearson correlation coefficient. If you just run a prog core, CORR, and you can, you'll be able to see the value of the Pearson correlation coefficient. And the other way is you can see from the variation inflation factor, which is the way to check the collinearity. So if you just put these two terms over together, you see there's a highly inflated value for the standard error. That means there's a high, because there's a high correlation between the two predictor variables, which lead to this collinearity problem. And the way to solve that is you use a centralized estimate for that. So for example, in this example, so you're going to use the centralized value, which is the age minus the mean age, and X bar is the sample mean. And also you use the quadratic terms of that centralized value. And then this way, you will be able to solve the problem of the collinearity. Like say, we will run this model again, and then the VIF is reduced to 1.04. It's almost no collinearity problem right there. And the Pearson correlation is going down to 0.21, but it's a negative 0.21. All right, so the other thing I want you to know in this topic is you should be able to do an ORF test. So this F test is similar to testing the model itself. And here the oral test, the whole test is testing you adding the quadratic terms together with the linear terms of age altogether. It's not testing. So this 2D freedom is not testing two separate random variables. They're actually testing the same random variable with the different forms, different polynomial forms. And here, if you use the centralized age as the predictor, you'll get this p-value less than 0.0001, which means it's significantly better than the null model. And then I also want you to be able to do the partial F test, especially for the higher order polynomials, because the higher order is important because the higher order one is not necessary, right? You can add them or you cannot add them, but the base one, the linear term of the predictor variable is necessary. So the testing for a higher order polynomial is especially important because if you reject the null hypothesis, that means it's not necessary for you to add the higher polynomial terms into the model. It won't improve the prediction power for that. So this is basically from SAS output is for the each terms, like say you have a t-test for the linear terms and you have a t-test for the quadratic terms. So for doing that task, it's actually just looking at the score for the score for that specific variables. And this is equivalent to the partial F test. You can see here, you're not going to get F value, but you're going to have a T value. But this T-score and P-value corresponding to that T-score is the same as you got for the partial F test. And keep in mind, SAS will not give you the result for automatically doing that partial F test. SAS will only do a ORF test. They won't give you to do the partial F test. So if you want to do the partial F test, you need to reference the lecture number 3, lecture number 4 lecture notes. So that means you need to run two models. One model is the model only including linear terms. The other is the model including both linear term and quadratic terms. And then you need to look at the sum of squares explained by the two models. And you need to calculate the difference in that sum of square. And then you need to calculate the p-values corresponding to that difference. So it's not very easy. You have to do them manually. SAS will output that. But the thing is, this is equivalent test. The t-test is equivalent to that partial F test for a higher order quadratic terms in this example. Okay, and then it really depends on if you reject null hypothesis for higher order terms. So if you fail to reject null hypothesis, and then you should be able to just use the linear terms there, like in this example. But if you reject the null hypothesis, and then you should include both linear terms and quadratic terms in your final model. But in this example, because we failed to reject null hypothesis with a p-value 0.19, then which means you should not include the quadratic terms. And your final model is just beta 0 plus beta 1 times the predictor variable x, which is the age in years. All right. And the last one I want you to know in this topic is testing the lack of fit. So testing the lack of fit is, in theory, if you have enough number of observations, you should, in theory, you should going up to a high quadratic terms up until we have the number of degree of freedom is k minus p. So you can, the highest order you can go is k. So k is determined by the total number of sample size n, and also the number of predictors p in the reduced model. So like I show in this example, based on the number of observations, we can actually go up until 23 degree of freedoms. So that means, except the linear terms, the lack of degree of freedom is 22, is 23 minus 1. So doing a test is simple. If you use SAS, you just need to use the option lack fit in your model statement of proc REG. Proc regression. So if you use the data set and put the model statement there, just like slash lack of fit, so SAS is already doing this lack of fit test. But the key thing is the interpretation for that part. So the lack of fit actually have the degree of freedom, as I said, automatically calculated based on the total sample degree of freedom, which is 27. 28 minus 1 is 27. Minus the possible number of values there, the error terms, and it calculates automatically. Just tell you the highest polynomial can go is 23, is h to the power 23, but it tests if this is necessary using this using the sum of square for that part. So this is going to be the sum of square explained by these 22 terms. So these 22 terms include h to the quadratic term of h cubic term, all the way up to h to the power 23. So that will have only this this mean square error equal to 94. And because the f value is too small, you reject a null hypothesis, which means there's not necessary for you to include this higher order polynomial on top of the linear terms. So that's the take-home message. Again, what I want to know is how to interpret this result, f values and p values from the lack of fit. But using the lack of fit option, you'll be able to test this very easily in SAS. All right, so that's all for lecture number 9. Any questions?
Yeah, I have a question for regarding the outliers. So if the outliers seem highly plausible, or let's say just plausible, maybe not highly plausible, will you include them in the model, or will you eliminate them to have a more fitting model for most of the data points?
You should remove them in the model fitting test because this may have impact for that. So this is why I call influential point. So inferential point may impact your final result. So if you, I mean, based on whatever benchmark, you can choose one, but you have to choose them beforehand. Like say, you can choose R student, but you have to say which use R student before you run the model. And if you base on that, because you see some of them may not indicate this inferential point, only the R student indicate this inferential point. But if you base on Cook D, this is not the inferential point. But once you specify based on this, you indicate this inferential point, you should remove them from the next from the later analysis.
Okay. Regardless if they're plausible because they impact the whole.
That's right. That's right. That's right. But think here maybe a little bit off your question is I want you to know because there are too many benchmarks you can use, too many metrics you can use. But which one would you like? Say you may have a contradiction. You know, you may have a contradictory result based on the threshold here, right? Like say based on both two, you will not reject, but based on this, you will say this is inferential point. I mean, you have to pre-specify one beforehand.
So it's
right.
Random.
Just make sure it's not data-driven, right? Because data-driven is going to be like kind of a cheating thing, but not just data-driven. Just specify one before the run analysis.
Gotcha. So it's not based on your own influence and your own.
That's right. That's right. Because otherwise, you can. I mean, it's based on you can choose either yes or no, right? I mean, but you have to specify one first.
Okay.
What? Excuse me. What if you have other outliers? Say you did leverage and you had outliers and jackknife too. You're allowed to remove all of them, correct?
Yes.
Okay.
But you still need to. I mean, it still have to depend on the specific question or your data set. Like say you have very small sample size, like say you only have 10 observations, like you cannot remove half of it, you know. Otherwise you may not have. It still depends on the specific situation.
Okay,
the
and
rule is you have to remove them before you do the analysis.
Okay, and let's say that you're working with a cubic model, kind of like the homework. When you're doing outliers, say leverage K would be 3.
Yeah.
And for jackknife, you would do 30 minus 3 minus 2? Well, 30
yes.
because that's a sample. Okay.
Right. Is actually based on the value in your data or for the model. It depends on that.
But just since it's cubic, K would be 3, and for jackknife, the second number, it would be, let's say your sample size is 30, would be 30 minus 3, and then minus 2.
Exactly. But
okay.
this may have very small impact here, but may have a big impact in the leverage. But the impact on the jackknife value will be small because it's only have impact of degree of freedom, and 1 degree of freedom difference is tiny. But here, like, one difference is relatively big. But again, it still depends on your n, right? Because if your n is too large, add the 1 here, I mean, add a small value. But if your n is too small, that influence will be large.
I also have a question regarding that. Because when I run the model for question 1 on the homework number 5, I found that I had like collinearity problems with the cubic model. So how can I remove that? Because I remember that you said on the lecture that we use the mean only with quadratic terms are present on the model. However, in here we only have, we have cubic terms. So can we do the same?
Yeah. You for the cubic term is not too far off, but if you have like too many numbers, like 23, doing that won't help a lot. But for like 2 or 3, it's okay. But for more than 3, actually, there's another method which is more advanced method. We're not going to cover in this, but you can still do centralized things. I think it's still there. The thing is actually you can easily evaluate that because after you feed the model, you see the VIF becomes smaller. It works. it is not very, it's kind of flexible. It's not there's no standard answers for that because you still have flexibility of using this different thing. But this is what I'm talking about here. It's just in general, the general rule. But I mean, specific to each question, there's still flexibility of doing different ways.
Okay, so then if we would encounter a collineated problem with the model on the homework, we could still use
That's right. That's right. Because,
okay.
Right, because the goal is to remove the collinearity. Right?
Okay.
Whenever it worked, it worked.
Okay, and then let's say that we test for the significance of the of the cubic term of the model, and we find that it's not significant at all. Do we still need to perform a lack of fit test, or we can just say that?
It depends on your goal, right? So if your goal is to see if you want to go even further by using a higher order of quadratic, so you can do a lack of fit. But if you think in your study plan, like say, you just think like the cubic term should be enough, then you should not do the lack of fit. But usually if you do a specific scientific question, you already have knowledge, right? From the previous literature and see if other people are doing that or not. So in doing the lack of fit is you have absolutely zero prior knowledge about the same study itself. Again, it's still specified to that your study question. But I mean, in terms of the exam, I would tell you, right? Because I want you to do a lack of fit, I would tell you to do a lack of fit. That's for the exam. But
okay.
if you've talked about your specific studies, I mean, against still depends on the context.
Okay.
Depends on the specific question there.
Then for the purpose of the homework, let's say that we didn't find like any significant, like I said, on the cubic term, we would still want to test whether higher order factors would be adequate for the model that we are actually studying or not, right?
Yes.
So we would still want to test for that. So we would still like perform an actual lack of fit test.
Yes, you can do that.
Okay.
Yeah.
Okay.
Sure. I think. All right. Let's just. I was hoping to like put the questions at the end, but let's just do a 10 minutes break for now. I mean, the last part is the lecture number 10. I guess you guys may have more questions for that, but you can maybe ask questions. Yes, go ahead.
I have a question in this lecture. So how can I know if the value is replicated or not? The replicated stuff.
If the value, say that again.
Replicated or not? The last slide before the last.
This one?
No, the previous one. The upper one.
Sorry?
The upper one. Yes, this one. How can I know if the data replicate or not? Replicates. 5 replicates.
So you have to, I mean, unfortunately, you have to evaluate manually.
Okay.
Say, or there be another easier way? If you want to sort your Y in your data, you only sort the Y variable. And then when you sort them, you can see similar number altogether, and that'll be easier for you to do that. But unfortunately, there's no automatic way. You still have to do them like kind of like manually.
Okay.
But this easy. The way just to sort them will help you a little bit, right? Because you can see them better.
I was gonna say, was there any way that you got that table? Was there any code that you can use to
no. For this table, no. For this table, because you still have to do it manually. This is not the automatic output from the result.
So, which data we have to evaluate? Is it X or X quadrate or the cubic one? Which data we have to evaluate?
No, doesn't matter cubic or not, but this is just the data, original data set. It doesn't matter you have cubic term or quadratic term. because you're not comparing your cubic term, you're actually looking at your y, the outcome.
Okay.
So for example, so for every x value, when x equals 39, there's 2 values corresponding to the 39. So the x values are the replicates, correct?
Right.
The 2 values corresponding.
Right, it's not cubic term, it's not, because you have same this, you have the same cubic term, right? You have the same quadratic term.
I'm not sure if you did it on purpose, but I noticed that when you show the replicates, you only give us one pair per number. So for example, 39, we have 2 numbers that are 39 for x, 2 that are 42. Anything special happens if you say have 3 numbers that are 39? So like 39,
Yeah.
1.
And then you just change degree of freedom to 2, right?
Okay, but when you're doing your
One.
equation, nothing happens, like d equals 29 minus 5, it would still be considered as one set of replicates?
Oh, no. This will increase that. So this 5 is actually the total number of degree of freedom. If you sum up degree of freedom.
Oh.
But if you have 3 replicates, the degree of freedom will be 2, right? And then this will become 6 instead of 5.
Okay.
Yeah, but this is a good question. Yeah, but in SAS you don't have to worry about, because SAS can identify that. But if you want to identify them manually, you have to do a table like this, and you calculate the degree of freedom. The key thing is the degree of freedom. It's not how many observations you have the same x.
Mm-hmm. Okay.
All right. So if you don't have further question in this topic, let's just do 10 minutes break and we come back with lecture number 10. I think I have to also stop my recording right there. Sorry, I have to leave the meeting because I have to put the recording in the first part. Otherwise, recording is too long. And then I will come back after 10 minutes around 3:40.